First off, some basic terminology. An encryption algorithm is often called a cipher with a C. The data we encrypt with a cipher is called the plaintext, and then what results from the cipher will get spit out, the scrambled form of the data, that is called the ciphertext. And do understand that the data to encrypt can be any kind of data. It could just be any arbitrary sequence of bits. It doesn't have to be text. Plaintext and ciphertext are just the traditional terms, likely stemming from the fact that encryption historically started out being all about securely transmitting text. In any case, in this example here, if we have the plaintext reading "socket to me!" and then we run that through an encryption cipher, we get out a ciphertext, which who knows what it looks like, just a bunch of bits, which in ASCII would probably look something like a bunch of garbage characters, maybe something like this. And then we run that ciphertext back through the decryption cipher, and we get back out the plaintext, so we get back the original message. So very importantly, notice that there's no apparent relationship between the ciphertext and the plaintext. If there were any apparent relationship, if there were patterns hinting at what the plaintext was, that would be a weak encryption algorithm. Ideally, the ciphertext should appear to anyone without the key to decrypt the ciphertext. It should appear to be total garbage. It should just look like random noise. Of course, it's not actually random. It's deterministically generated by the encryption algorithm. It just has the appearance of being random because it's so scrambled. Also understand here that in some cases you have encryption algorithms where the decryption process is precisely the same. In other cases, though, the encryption process may differ. So in reality, an encryption algorithm may actually be a pair of algorithms, one for the encryption, one for the decryption. Perhaps the simplest cipher around is probably also the oldest, and it's called the Caesar cipher because it was actually used by Julius Caesar. Though extremely simple, it was probably pretty effective at the time because, first off, most people back then couldn't read. Moreover, even amongst those who could read, the very idea of encryption was probably unfamiliar to most. The way the cipher works is you simply substitute each letter of a message with the letter which is some set places down in the alphabet. Caesar reportedly used a rotation of 3. So in the English alphabet, a B would be substituted with E, C with F, D with G, E with H, and so forth. And then once you get to the end of the alphabet, what you do is you simply treat it as if the alphabet wraps around. So the letter Z, for example, would substitute with C. And then, of course, to decrypt, you would just do the opposite. You would take your C's and you'd turn them back into Z's. So, assuming some undesired party gets a hold of your ciphertext, if it doesn't occur to them that they're looking at a message encrypted with a Caesar cipher, then they'll just dismiss it as a bunch of random garbage. If it does occur to them, though, and they really want to read your message, you're probably screwed, because it's really easy to crack a Caesar cipher. You just really go through all 26 possibilities, because there's only so many rotations that you might have used. So the Caesar cipher is not very secure, but it does demonstrate one of the basic principles of many encryption schemes, which is called substitution. You take the basic units of your plaintext, in this case letters, and you substitute them according to some table of this gets substituted with that. This same basic mechanism, substitution, is what's used with secret decoder rings. Each letter is arbitrarily mapped to another letter, or in some cases to numbers, and the recipient just needs an identical decoder ring so they can reverse the substitution. Now, having to use a physical object, a decoder ring, as a key is kind of clumsy because it means you have to distribute these physical objects to all the people who need to communicate with each other. It would be much more convenient if we could base our shared secret on just a short piece of data we can exchange, in other words, a key. A really simple way of doing substitution based upon a key is to line up our secret random key with the start of the alphabet, such that here, when our key is ZDXWEJKR, and note for simplicity here, we're just dealing with capital letters, so ignore lowercase letters for now. Here, A gets substituted with Z, B with D, C with X, D with W, and so forth until H with R. And then as for the remaining letters I through Z, what you do is you just fill in all the remaining letters that weren't included in our key. You fill them in left to right in sequence. So all the letters we didn't use were A, B, C, F, G, H, I, L, M, N, O, P, Q, S, T, U, V, Y. And so we substitute I with A, J with B, K with C, L with F, M with G, and so forth. So, assuming you and I both have settled upon this mechanism for encryption, all I have to do is share with you the random key I've chosen, and then I can send you messages and you can decrypt them with the same random key. And you would just build your substitution table just like so. You'd line up the key first with the start of the alphabet and then fill in the remaining letters, and then you get your substitution table. So substitution is a basic and really quite obvious technique of encryption. Another similarly obvious and simple technique is what's called transposition, which is the fancy term for taking the pieces of our plaintext and scrambling them around. Not scrambling them randomly, of course, scrambling them in a deterministic fashion that can be reversed, but nonetheless scrambling them around. So in the ciphertext we have the appearance of randomness. Perhaps the simplest kind of transposition is columnar transposition, so called because it's as if we take our message and write it in a set number of columns, here 4 columns, and then we get our ciphertext by reading down each column. So our plaintext, I like zebras, we write that out in 4 columns, and then we simply read down each column in turn. So we go IKES space EB period, L space R space IZA space. Note that we got a little bit of distortion because our original plaintext didn't have 2 spaces at the end. The period is the end of the message. We can correct this distortion by simply including with the ciphertext a note of precisely how many characters long our message actually is. That way, when we decrypt, we know that the last 2 characters, those last 2 spaces, weren't really part of the message. Now, of course, even when you do this on paper, you don't really have to write out the columns. We can simply start at the beginning of the plaintext and skip over every 4 letters. And once we go past to the end of the message, we just go back to the start, but then start at the next letter over for effectively the next column. Now, of course, while in this case we used 4 columns, we could use any other number of columns, except of course 1, which would result in the ciphertext identical to the plaintext. Nor would you want a number of columns equal to the length of the plaintext or greater than the plaintext, because then again you'd get a ciphertext identical to the plaintext. Whatever number of columns we decide to use, that's the key for our message. You and I want to exchange messages and we've agreed to use columnar transposition. The secret key we then share is how many columns. A one-time pad is another simple encryption technique in which we use a key which is as long as the plaintext itself. And remember, keys are supposed to be random so that they are unguessable. What we do with the key is combine a character of the key with a corresponding character of the plaintext. This combination, though, of course, has to be reversible. So, for example, addition is a good candidate, because we can add a character of the plaintext to a character of the random key and get out a character of ciphertext, and then to reverse that we use subtraction. We subtract a character of the random key with the corresponding character from the ciphertext, and we get back the corresponding character of plaintext. Another good operation to use is an XOR, exclusive OR, which has the handy feature of being its own inverse operation. So we XOR together a character of plaintext with the corresponding random key character, and we get out a ciphertext character, and then to reverse we again just use XOR. We XOR a random key character with a corresponding ciphertext character, and we get back a plaintext character. In either case, if we use addition or an XOR, what we get out is a ciphertext that should actually be perfectly random, or at least as perfectly random as our random key. And in fact, one-time pads are actually the only form of encryption known to be totally secure, at least in theory. As long as the keys used are truly random and they are kept secret, there's really no possible way to crack the code. Unlike with any other encryption technique, there are really no clues left in the ciphertext for a cryptanalyst to analyze and discover some pattern. Aside from the length of the message, or rather the maximum length of the message, there's really no information about the plaintext that's carried over into the ciphertext. So if one-time pad is perfectly secure in theory, why are they not used in practice? Well, the downside is in having to generate and distribute and keep secret keys which are very, very long. And be very clear that you shouldn't reuse keys. This is generally the case with most encryption except public key encryption. If an attacker intercepts 2 messages encrypted with the same key, there are cryptanalysis techniques that can exploit that. So while one-time pads were historically used for high-grade military security, the technique is really not practical for most other uses. Managing and keeping track of and keeping secure your keys is of course extremely important, and generally the shorter the keys, the easier this is to do. Just imagine, say, the hassle if you want to transmit a gigabyte-sized file using a one-time pad. You'd have to generate, store, and distribute a key which is over 1 gigabyte in size, and that's just not very practical. What's called a stream cipher in the end operates very much like a one-time pad, with the difference that we use a small key, something like 128 bits or 256 bits, something about that size, and from that the stream cipher generates what we call the key stream, which is the actual key we are combining with the plaintext to produce our ciphertext, just like we do with a one-time pad. So the big advantage here over the one-time pad is that we are using small keys. The strength of the encryption, though, is not as theoretically secure, because pseudorandom is not the same thing as random. Though a pseudorandom stream of data may appear random, it's not truly random, it's actually deterministically generated from some starting point, in this case the key. The determinism means that yes, there are patterns. The question is, how apparent are those patterns? How easy are they to discover with techniques of cryptanalysis? Stream ciphers also share the weakness with one-time pads that they are especially vulnerable to attacks if an attacker gets their hands on two messages encrypted with the same key. So while with symmetric encryption it's always true you want to avoid reusing keys, with stream ciphers it's especially true. I should note that in some people's use of the terminology, one-time pads are considered a kind of stream cipher, just one in which the key stream is truly randomly generated rather than pseudo-randomly generated. In contrast to stream ciphers, we have block ciphers which encrypt messages in fixed-size chunks, and these chunks are encrypted independently. So in fact, if you have two chunks in your plaintext which have identical content, the ciphertext for those chunks encrypted with the same key will be identical. Now, whereas a stream cipher always uses a pseudo-randomly generated key stream, this is not the case in most block ciphers. Most block ciphers are based on the techniques of substitution and transposition, although pseudo-random generation does play a role in some block ciphers. And so in some cases the distinction between block ciphers and stream ciphers can become a bit blurry. Some people try to make a distinction, falsely I think, based on just the names of stream versus block, that a stream handles the encryption byte by byte, unit by unit, character by character, whereas a block takes things in set chunks of, like, say, 512 bits at a time. But I don't think that's actually a very meaningful distinction, because after all, the choice of byte-sized units or character-sized units is just another arbitrary unit size for a block. So by this way of thinking, a stream cipher could just be a block cipher that uses very small blocks. For that reason, I think the more meaningful distinction is that stream ciphers use pseudorandom generation, whereas with block ciphers that may be an element of the encryption, but it's not the whole thing. Probably the three most widely used block ciphers are the three standards. First, the old DES, meaning Data Encryption Standard, which used 56-bit keys, and then the update of that, triple DES, which, as the name implies, uses triple-sized keys, 168-bit keys. And then there's AES, which was introduced in the last decade and uses 128, 192, or 256-bit keys. DES, with its 56-bit keys, these days is really quite inadequate for reasons we'll discuss later. In short, a 56-bit key is really just too small. So a lot of institutions in the past that use DES, like banks, these days most of them are using triple DES, which is significantly more secure, but allows those institutions to carry on with some of their old infrastructure, their old hardware and software. For anyone without any legacy concerns, you would almost certainly go with AES over triple DES. We'll discuss the details of AES in a moment, but recall that I said with a block cipher, two identical blocks in the plaintext are going to come out encrypted the same when you encrypt them with the same key. As you might imagine, that's really quite problematic because it leaves a huge clue to any attacker of, hey, these parts of the ciphertext represent identical parts of the plaintext. Much worse, you've effectively given the attacker many small independent messages that have all been encrypted with the same key, and like we said earlier, that leaves your ciphertext vulnerable to cryptanalysis techniques. To correct for these faults, we only use block ciphers with what are called modes of operations. There are several of these, including 5 we'll look at, starting with electronic codebook, or ECB, cipher block chaining, or CBC, cipher feedback, or CFB, output feedback, or OFB, and counter, abbreviated as CTR. All of these, with the exception of ECB, electronic codebook, allow for the secure use of a block cipher with a single key on a message longer than a single block. The strangely named electronic codebook mode is not secure because it's the mode in which we do nothing special. We just simply encrypt each block straight with the key, and that's it. So ECB, in a sense, is the do-nothing mode. But in CBC, cipher block chaining, we start off with, in addition to our random key, an additional random piece of data called an initialization vector, which is a block-sized chunk of random data. Like the key itself, the IV will be necessary for anyone to decrypt our message. The difference, though, is that initialization vectors generally don't need to be kept secret. In fact, we very often just tack it on to either the front or the end of our ciphertext. In any case, the way CBC, cipherblock chaining, works is that we start by XORing the first block of plaintext with the initialization vector. That's what the circle with the cross is indicating in XOR operation. The product of that XOR is then what gets encrypted with the key for our first block. And then that first block of ciphertext produced from this, that is what we use to XOR with the next block of plaintext. And then that result of the XOR is what we encrypt for the second block. And again, we get a second block of ciphertext. And then again, that second block of ciphertext is XORed with the third block of plaintext. And then that XOR of the plaintext and the ciphertext is what gets encrypted for the third block of ciphertext. So every block of ciphertext is used as an input to XOR with the next block of plaintext. So effectively what happens in cipherblock chaining is that our plaintext is getting modified before encryption. First it's modified in the first block with the IV, and then each successive block is modified by the ciphertext of the previous block. Effectively then, blocks of our plaintext which are identical don't get encrypted as identical, they first get XORed with the preceding ciphertext. Now note that in cipherblock chaining, encryption of each block depends upon first having encrypted the previous block. So the encryption has to be done sequentially. The same is not true when decrypting cipherblock chaining. The inverse of what we did when we encrypted is to first decrypt the individual block of ciphertext, and what we decrypt then simply has to be XORed with the preceding block of ciphertext to get out the block of plaintext, with the special case of the first block where we XOR with the initialization vector. So actually note with cipherblock chaining, if you lose your initialization vector or for some reason it gets scrambled or whatever, you can still decrypt your message except for that first block. In the CFB mode, cipher feedback mode, we again use initialization vector, but this time we actually start off by just encrypting the initialization vector itself. The result of that then we XOR with our plaintext to get our first block of ciphertext, and then it's actually that first block of ciphertext which we encrypt in our second block, and then the result of that we XOR with the second block of plaintext to get our second block of ciphertext. And then again we take that second block of ciphertext, encrypt it, XOR it with the third block of plaintext to get our third block of ciphertext. So very strangely here, in this mode, we're not actually running our plaintext through the block cipher. But of course, what will come out of the block cipher will have high entropy, it'll be very random. So just like in a one-time pad or a stream cipher where we have our random data which we XOR with our plaintext to get our ciphertext, we're kind of doing the same thing in this mode. The block cipher in this mode is sort of being used as a pseudo-random number generator, which is one reason I said that the line between block ciphers and stream ciphers isn't always stringently defined. Now, to reverse this process to decrypt, we get each block of plaintext by taking the ciphertext of the previous block and actually encrypting it, not decrypting it, encrypting it, and then XORing that with the ciphertext for that block. So for example, to get our last block of plaintext, we take the previous block of ciphertext, encrypt that, and XOR that with our last block of ciphertext. And note, of course, the special case of our first block where we don't encrypt with the previous block because there is no previous block. We encrypt the initialization vector, and that is what we XOR against the first block of ciphertext to get the first block of plaintext. So the cipher feedback mode has the fairly cool property of using just an encryption cipher without any corresponding decryption cipher. And again, like in cipherblock chaining, whereas encryption must be done sequentially, decryption can be done in parallel. You can do each block independently, because decryption of each block only requires the ciphertext of the previous block, which we already have because we're decrypting rather than encrypting. When we encrypt, we also need the previous block of ciphertext, but of course we don't have the previous block of ciphertext until that block itself has been encrypted, so the encryption must be done sequentially. One last small advantage of cipher feedback over cipherblock chaining is that because we're not actually running our plaintext through the block cipher, we're just using the block cipher to generate pseudorandom data to XOR against our plaintext. What this means is that we don't have to pad out our last block. With cipherblock chaining, if our data isn't evenly divisible by the block size, then that last block has to be padded out. And so that requires some scheme of denoting in our ciphertext how long the plaintext actually is and how much is just padding. With CBC, with cipher block chaining, our ciphertext can be precisely as long as our plaintext. We don't have to pad it out. The output feedback mode is very similar to the cipher feedback mode, with the one difference that what we use as input to the block cipher is not the preceding block of ciphertext, but the preceding output from the block cipher. Hence the name of output feedback rather than cipher feedback. Understand that cipher is sometimes confusingly used as a synonym for ciphertext, so in cipher feedback, cipher refers to the ciphertext. Anyway, the basic principle here is the same. We're effectively generating a pseudo-random stream of data, which we are then XORing against our plaintext to produce our blocks of ciphertext. The advantage of output feedback, though, is that we can actually generate that entire pseudo-random stream before we even involve the plaintext at all. This means we can actually do the bulk of the work ahead of time before we even have a plaintext. We can just randomly pick keys and initialization vectors and generate a whole bunch of pseudo-random data to use later on. And that's extremely helpful performance-wise in certain scenarios. Like, say, for a bank that has to do lots of encryption all the time. With the output feedback mode, the hard work of the encryption can be offloaded to one part of the system that just churns out key streams all day. And when another part of the system actually needs to do some encryption, it can just grab one of those key streams and do its encryption simply with an XOR. And note again that in this mode and in the cipher feedback mode, the distinction between a stream cipher and a block cipher becomes extremely blurry. And last thing about output feedback is it has a nice advantage that the decryption process is precisely the same as the encryption process. We just swap in the ciphertext in place of the plaintext. The counter or CTR mode is another stream-like mode of operation. This time, though, the initialization vector, for fairly obscure reasons of technical terminology, is generally not called the IV, it's called the nonce. Yet it's the same idea. It's a random block-sized piece of data. And just like in output feedback and cipher feedback, our goal here is to generate a pseudo-random key stream based upon this random input and our key. And as usual, we get our first block of the key stream by simply running it through the block cipher. To get our successive blocks of the key stream, though, this time in counter mode, we simply modify the nonce according to some simple function, most commonly a function that simply increments the nonce, hence the name counter. Now, for some time there was some concern about this counter mode that using a simple function like just incrementing our nonce would make our key stream too predictable. These days, however, it's generally accepted because it's recognized that the true randomness of the key stream should be provided by the block cipher, and any good block cipher should have a radically different output when you make just a small change in the input, which is what happens when we increment our nonce. So here, for example, when our nonce starts in hex C59BCF35 something 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 and then ends in a 0, the output of that run through our block cipher should be totally unrelated to what we get when we run C59BC535 something 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 1 through the same block cipher with the same key. If that's not the case, then that's a weakness of the block cipher itself, and we have deeper problems than a problem with our mode of operation. So, a simple incrementing function is most commonly used in this mode, though alternatively you can use any function as long as that function produces output that doesn't repeat, or at least doesn't repeat for a very long time. The goal here, of course, is that the input to the cipher in each block is unique, so there's no two blocks that get the same input to the cipher. Note that the counter mode shares with output feedback the property that the key stream can be generated entirely ahead of time. But note that it also has the advantage that the key stream can be generated in parallel. It doesn't have to be generated in sequence. So now, looking at an actual block cipher itself, AES, the Advanced Encryption Standard, as I mentioned, is today's predominantly used symmetric encryption algorithm. However, the algorithm itself in the standard is actually called readable, which is a portmanteau, a word combination, of the names of the two creators of the algorithm, two Belgians, Joan Damon and Vincent Ryman. I believe that's how it's pronounced, R-I-J-M-E-N. This readable algorithm was actually selected in a contest. There was a years-long selection process in which several candidates were scrutinized, and in the end, readable is the one that was selected in 2001. And it was selected not just for the integrity of its encryption, but also partly because it offers pretty good performance. which is fairly important in an encryption standard, particularly for high-volume use cases, like say what a bank does. You want the encryption and decryption to take as little time and computing resources as possible. While the Rijndael algorithm itself will allow for block sizes and key sizes of 128 up to 256 in increments of 32, so 128, 160, 192, 224, and 256, those are all valid block and key sizes. In the AES specification, the blocks are always 128-bit, and the key is a choice of 128, 192, and 256 bits. Now, of course, the size of the key determines how many possible keys there are. Given a size of 128 bits, that means that there are 2 to the 128th power possible keys, which is a hell of a lot. And then, likewise, a key size of 192 bits gets you 2 to the 192nd power number of possible keys, and 256 bits gets you 2 to the 256th power possible keys. And those, of course, are even more fantastically astronomical numbers. Now, given today's existing computers, it is presumed that 128 bits is actually perfectly adequate. It is not really foreseen that even if we see the same kind of performance increases in computers in the next, say, 30-40 years that we've seen in the past 30-40 years, it's not foreseen that enough computing power will be there to do a brute force attack on Rijndael encryption using 128 bits, because 2 to the 128th is really just a hell of a lot of possibilities. So if an attacker wants to brute force their way to find your key, that is, by just going through all possibilities until they hit the right key, there just aren't today computers fast enough to really do that in a practical amount of time. Practical here meaning within a person's lifetime. On the other hand, there may be some disruptive developments in computer technology coming down the line, namely what are called quantum computers. If quantum computers become a reality, then there are algorithms which would cut down the effective key size in half. So something encrypted with a 128-bit key would be as susceptible to brute force attack as a 64-bit key. So this is the main reason why the standard also allows for 192-bit keys and 256-bit keys. If you're dealing in highly sensitive data, like say military secrets, you probably don't want those secrets decrypted even a few decades from now if quantum computing becomes a reality. For less sensitive usage, just say like for personal usage or consumer usage, 128-bit keys are generally considered perfectly fine. It's just a fact that most stuff most people encrypt isn't really all that important for an attacker to keep around for decades on the off chance that one day they'll be able to, with great effort, decrypt it. In any case, the way Rijndael works, both when encrypting and decrypting, is to first take the key and from it, by a series of computations, produce what's called the key schedule. This key schedule is effectively really just a longer key. It's taking the short key and producing from it a longer key, including portions which will be used like a substitution table. So once we have this key schedule, the actual encryption and decryption is done in a series of rounds. For 128-bit keys there are 10 rounds, for 192 there are 12, and for 256-bit keys there are 14. In each round we are taking the input and transforming it in a series of operations, just like we saw in the simpler ciphers where we used substitution, transposition, and also combination with a key, usually with an XOR operation. In Rijndael, in each round, we use one or more of these four operations, which we call subbytes, shift rows, mixed columns, and add round key. Described briefly, in the subbytes operation, we are doing a substitution of each byte with another in a lookup table which is a part of the key schedule. The shift rows operation is a transposition operation where we take rows of the state here referring to the current state of the bytes of our data. We take each row and we shift them cyclically a certain number of steps, which is specified by the key schedule. In the mixed columns operation, a different kind of transposition is formed, one using what's called a linear transformation, and I won't go into the details. And then finally, in the add round key operation, each byte of the state is combined with the so-called round key, which is a part of the key schedule, using a bitwise XOR, just like in stream ciphers or in a one-time pad. Now, whether we have 10, 12, or 14 rounds to perform based on the size of the key, in the first round we have 5 operations: first add round key, then subbytes, then shift rows, then mixed columns, and then one more add round key. in all subsequent rounds, we drop that first add round key operation, just doing the subbytes, shift rows, mix columns, and add round key operation, except then in the last round, we also drop that mix columns operation and tack on an additional subbytes, shift rows, and add round key operation. So the basic principle here, again, is that if a little bit of substitution and transposition is good, well, to get even more security, to get even more apparent randomness, do a lot of substitution and transposition, and mix them up in different orders. Now, why it's better to do these operations in this particular order is a matter of mathematical analysis. The real trick in designing encryption algorithms is generally not so much in coming up with some combination of the basic techniques like substitution and transposition, but rather the difficulty is in proving that the particular substitutions and transpositions and XORing that you're doing is actually effective, that it is actually increasing the randomness of the output rather than doing no good or possibly even being counterproductive. It's actually quite possible to do additional operations of transposition and substitution that actually detract from the strength of your encryption. So that's a good reason why you don't try and roll your own encryption algorithm. Creating an algorithm isn't hard, but creating one that stands up to real scrutiny definitely is. In an earlier unit, we explained hash functions. A hash function is a function which takes any input value and returns a generally smaller value within a finite range called a hash. Most commonly, a hash function is used like a kind of sieve that says these inputs go into this bucket, these inputs into that bucket, these inputs into that bucket. And most commonly the intention is for input values to get more or less evenly distributed between buckets. So with a good hash function, generally any hash output is equally likely for any random input. Now, because the set of possible inputs is generally infinite, like say if we allow numbers as input, then well, there are an infinite number of numbers, and because the return value, the hash, is within a finite range, this means that different inputs will produce the same hash. Like say, if you get the hash value 5 when you input the value 73, but then you also get the output hash value 5 when you input the value 929, well then for that particular hash function, the values 73 and 929 produce a hash collision. Now, what's called a cryptographic hash function is a hash function with special properties, including the property that given a hash, you cannot, as a matter of practicability, find one or more inputs that produce that hash. Cryptographic functions also have what's called a strong avalanche effect, meaning that any small change to an input data is going to result in a very different hash, one that doesn't seem to bear any relation to the other. So here, for example, if we have two input strings, Sakatumi exclamation mark and Sakatumi question mark, the two cryptographic hashes we get from these inputs are totally different. There's no apparent relationship. They're not even remotely close values. More formally, the desired qualities of a cryptographic hash function are called pre-image resistance, second pre-image resistance, and collision resistance. Pre-image resistance refers to what we first discussed, that given some output hash, it is very, very difficult, in fact infeasible, to find any input that produces that hash. Second pre-image resistance refers to the property that if you have both an input and its hash, it is difficult to find some other input that's going to produce that same hash. And then lastly, collision resistance refers to something subtly different in that we don't have any particular input we want to find a hash for. We just want to find any two inputs that produce the same hash. And that as well is something that should be infeasible to do with a cryptographic hash function. So now the question is, what is a hash function with these properties good for? Well, one very useful application is as a data integrity check. If Nathan wants to send a file from his machine to Kate's machine, and Nathan and Kate want to verify that the file Kate receives is in fact the precise file Nathan intended to send, well then, in addition to sending the file, Nathan runs the file through a cryptographic hash function, gets that hash, and sends it to Kate, and then Kate can run the file she received through the same cryptographic hash function, and when she compares what she gets out of the hash function herself and what Nathan sent her, those two hashes should match. But if Kate's copy of the file doesn't match Nathan's copy bit for bit, then the hash Kate computes won't match the one which Nathan sent her. Now, of course, it is possible that the hash which Nathan sends could get corrupted along the way. Data corruption does happen, and it very well may happen to the cryptographic hash when it is transmitted, just like data corruption can happen to the file itself. However, it is exceedingly unlikely, like more than astronomically unlikely, that both the file and the hash will get corrupted in such a way in transmission that the corrupted file run through the hashing algorithm will match the corrupted transmitted hash. I mean, it is a possibility, but it's so unlikely you might as well be more concerned about getting struck by meteors. It's also possible that the hash might get corrupted, but the file not corrupted, in which case when Kate checks the hash, she's going to get a false negative. The hash she receives isn't going to match the hash which she produces, and so she's going to assume that the file that she received is corrupted, even though in this scenario it's just the hash that got corrupted. Now, such a thing can happen. It's not as likely, of course, though, as the file itself getting corrupted, because the hash is generally much smaller than the file, so there are just fewer bits to get corrupted, and a false negative generally isn't as harmful as a false positive. The false negative means that Kate's going to erroneously tell Nathan that she needs him to resend the file, even though she already has the right file. Now, another concern is that the data of the file and the hash might not just get corrupted in transmission, but actually tampered with by some attacker. If an attacker can perform a man-in-the-middle attack, meaning they can read and intercept the data as it's transmitted, the attacker could erroneously modify the file or send a completely different file and just erroneously send Kate the wrong hash, one which matches the malicious file. So because of such attacks, a cryptographic hash just transmitted along with the file won't protect you from tampering. It's okay to send the file itself through the unsecure channel, assuming either you don't care if anyone else reads your data or if it's encrypted, but the cryptographic hash should be sent through a secure channel. Like, say, if Nathan just wrote down the hash on a piece of paper and then handed it to Kate in person. That would work, though obviously it's less convenient. But however you do it, if the authenticity and integrity of the hash itself can be assured, then when Kate performs the check, when she runs the received file through the algorithm and checks the output against the hash she received, if they match, then she knows for sure that this is the file, bit for bit, which Nathan intended to send to her. Three of the most commonly used cryptographic hashing algorithms are called MD5, SHA-1, and SHA-2. The MD in MD5 stands for Message Digest, and this is the fifth iteration of an algorithm. MD4 was the predecessor, which was shown to be insecure, and so MD5 was developed about in the early 90s. It produces 128-bit hashes, and then the SHA-1 algorithm is so called because it stands for Secure Hash Algorithm, and it produces 160-bit hashes. And then several years ago, when SHA-1 was shown to have some weaknesses, SHA-2 was introduced, which confusingly is not one single algorithm. That's why there are different variants that produce different sized hashes, including as low as 224, but as high as 512 bits. And obviously the more bits, the more secure, at least in theory. Whether it makes a difference in practice probably depends on what you're doing, really. For most purposes, 256 bits is probably perfectly adequate. Of these three here, MD5, SHA-1, and SHA-2, SHA-2 is the safe choice. It's the most recent standard. MD5 has been shown to have weak collision resistance, which doesn't matter in all applications, but in some applications that's important, so keep that in mind before using MD5. Now, I won't go into the details of any of these algorithms. As you might imagine, it involves a lot of sort of substitution and transposition and rounds, much like in our block ciphers. The difference here that we are reducing arbitrarily sized input down to one small piece of data. An asymmetric or public key encryption algorithm is one which uses two keys to do encryption and decryption rather than just one. These two keys are not just randomly chosen independent of each other. There actually has to be a special mathematical relationship between the keys, so they instead are generated together in a pair by an algorithm. And that algorithm, of course, takes random input, so it doesn't produce the same pairs of keys every single time. The special relationship between the keys is that when we encrypt with an asymmetric algorithm, we encrypt with one of the keys and then decrypt with the other. One is designated as the public key and the other as the private key. When we encrypt with the public key, then the ciphertext can only be decrypted with the corresponding private key. And with some algorithms it works the other way too. Encryption with the private key can only be decrypted with the public key. The reason one of the keys is called the public key, and the reason this is sometimes called public key encryption, is because this scheme allows us to publicly disclose one of the keys. It's something we can just publish to the world, rather than keep secret. And in fact, in many applications of public key cryptography, that's precisely what we want to do. We want everyone to have our public key. What this allows is two things. If I generate a pair of keys and then publish the public key to the world, anyone with my public key can encrypt something such that only I may decrypt it, because I'm the only one with the corresponding private key. Another application is that with my public key out there and known in the world, I can encrypt something with my private key, which of course anyone in the world could decrypt because everyone has my public key, but this way everyone is assured that the encrypted message is actually from me, because I, as the only holder of my private key, am the only one who can encrypt something such that it can be decrypted with my public key. It's exceedingly unlikely that you could run any old bits through the decryption cipher with my public key and get out anything resembling coherent data. So if you do get coherent data, that's a very strong assurance that it is something which I encrypted. Now, as we'll go over when we discuss RSA, the most commonly used public key encryption algorithm, asymmetric encryption tends to be significantly less efficient than symmetric encryption. Therefore, the most common use of public key encryption is actually to exchange symmetric encryption keys. The protocol for this works like this. The receiver of the symmetric key, first off, has their own asymmetric key pair, and assume that the receiver's public key is out there in the world where the sender can get at it, like say it resides in some public directory on the internet. So the sender generates the symmetric key they wish to share with the receiver, and they encrypt it using the receiver's public key. They then transmit to the receiver that encrypted message, and the receiver can then decrypt it with their own private key. So now the sender and receiver have a shared secret, this shared symmetric key, which they exchanged over an unsecure channel, like say the internet. There's actually one flaw here though, and that is that the receiver has no guarantee that they haven't been duped by a man-in-the-middle attack, by someone intercepting their encrypted communication, because it's quite possible that that man-in-the-middle intercepted the sender's key, and even though the attacker can't decrypt it, what they can do is prevent it from reaching the receiver, and they can instead send to the receiver a false key, because this interceptor, the attacker, like everyone else, has access to the receiver's public key. So the attacker can generate their own symmetric key, encrypt that with the receiver's public key, and then send it to the receiver. And there on out, the attacker can carry on communication with the receiver in the guise of the sender. To prevent this attack, we complicate our protocol a little bit. First off, both the sender and the receiver have their own asymmetric key pairs with each other's public keys somehow known to each other, like say through a public directory. As before, the sender generates a symmetric key and they encrypt it with the receiver's public key, but before sending it, they also then encrypt it with their own private key. This means the recipient is going to have to first decrypt with the sender's public key and then decrypt with their own private key. This added layer of encryption doesn't keep out eavesdroppers, but it authenticates that the receiver is getting this message from the intended sender. The most widely used public key cryptosystem is called RSA, which stands for Rivest, Shamir, and Edelman, which are the names of the three inventors. The keys used in RSA can be arbitrarily large, and the larger the key, the more difficult the encryption is to crack, but also the longer it takes to do encryption and decryption. And asymmetric encryption and decryption, as I mentioned earlier, does tend to take a lot longer than plain old symmetric encryption. In practice, the keys used with RSA typically fall in the range from 1024 to 4096 bits. And note that these sizes are significantly larger than anything we would use today in symmetric encryption. I won't get into the math of RSA as I barely understand it myself, but in short, the system revolves around the difficulty of factoring large prime numbers. The secret key in RSA is the combination of two large prime numbers, and then the public key is the product of those two primes. Given any large number, it's a difficult mathematical problem to find two prime factors that make up that number, so it isn't feasible for someone given the public key to determine in a reasonable amount of time the secret key. Now, because RSA, like all public key encryption systems, is quite slow relative to symmetric encryption, the most common use of RSA is to exchange symmetric keys. Even on a modern system, encrypting and decrypting, say, a large file, would be very slow with a public key system like RSA. We'll end now with a brief discussion of how encryption gets broken. Cryptanalysis refers to the art and science of extracting hidden information from a system. One approach with encryption is to apply mathematical techniques, including differential analysis, integral analysis, linear analysis, related key attacks, and other such techniques. But aside from such sophisticated approaches, the simplest way to go about breaking encryption is a brute force attack, meaning simply trying all the possible keys. But of course, any decent encryption system uses large enough keys to make this infeasible. Even a smaller key by today's standards, like a 128-bit key, well, 2 to the 128th power is a very, very, very large number. So large, in fact, that given all the computational resources in the world at your disposal, you probably still couldn't search through all of the keys in anything like a reasonable amount of time. I think even the low-end estimates of how long that would take are somewhere in the range of millions of years. So for encryption systems thought to still be secure, we don't really worry about brute force attacks. For a system with a weakness, however, that means there's some kind of mathematical technique which allows us to cut down on the key space that has to be searched, thereby possibly making brute force attacks feasible. For example, if a technique were discovered to cut down the effective key space we have to search from a 128-bit space down to a 64-bit space, and remember we're dealing in powers of 2, so that means cutting the key space down in half 64 times. 2 to the 64th power is a much, much smaller number than 2 to the 128th. If an exploit were discovered that cut down the key space from 2 to the 128th to 2 to the 64th, then a brute force attack on the remaining key space becomes feasible. And actually this is a common thing with mathematical techniques. They don't necessarily discover the one true answer directly, they rather simply cut down the size of the key space that has to be searched, and then a brute force attack on the remaining key space is what finds the actual key. Cryptanalysis doesn't have to limit itself to only dealing with the ciphertext. There are other ways of getting at hidden information, what are called man-in-the-middle attacks and side-channel attacks. A man-in-the-middle attack refers to any situation where the attacker intercepts data as it's being transmitted. This can mean more than just listening into the communication, but actually interfering. The attacker replaces data being sent with its own data, such that one or both of the communicating parties gets data from the attacker in place of data from their correspondent. By doing so, the attacker might fool one of the two correspondents to send them sensitive data, or the attacker might inject malicious data, and maybe even infect the targets with malware. A side-channel attack exploits the fact that cryptosystems run on actual physical hardware. They're not just abstractions in software. By monitoring the power consumption of a system, watching the timing of the system, how long it takes to perform certain tasks, looking for remnant data on storage mediums which the users thought had been deleted, but in fact still contains clues, remnants of what the data on that medium was. All of these are side-channel attacks, and it's often very surprising what you can learn from a system in unexpected ways. For example, you can statistically analyze how a system uses power when it performs encryption, and then use those statistics to make educated guesses about which keys are being used when a system performs encryption or decryption. So it's another technique that can be used to cut down the key space that has to be searched in a brute force attack.